Welcome to today's paper reading. Today's paper is titled, In Defense of RAG in the Era of Long Context Language Models. This paper was published on the AR14 preprint by Tan Yu, Anbang Su, and Rama Akkiraju from NVIDIA. The abstract discusses the comparison between retrieval-augmented generation, RAG, and long-context large language models, LLMs. While RAG has been effective for context-based answer generation, recent advancements in long-context LLMs have shown superior performance in long-context applications. However, the paper argues that long-context LLMs may suffer from a lack of focus on relevant information, potentially degrading answer quality. To address this, the authors propose an order-preserved retrieval-augmented generation, OPRAG, mechanism, which significantly enhances RAG's performance in long-context question-answer scenarios. The study finds that OPRAG initially improves answer quality with increasing retrieved chunks, but then declines, forming an inverted U-shaped curve. There are optimal points where OPRAG achieves higher quality answers with fewer tokens compared to long-context LLMs. Extensive experiments demonstrate the superiority of OPRAG over long-context LLMs. Figure 1 illustrates the performance comparison between the proposed order-preserved retrieval-augmented generation, OPRAG, and long-context large language models, LLMs, without RAG on the en.qa dataset of Infinity Bench. The OPRAG, utilizing Llama 3.1-70b as the generator, demonstrates a significant advantage over its counterpart using Llama 3.1-70b without RAG. Specifically, with only 16K retrieved tokens, OPRAG achieves an F1 score of 44.43, whereas Llama 3.1-70b with the full 128K context achieves an F1 score of 34.32. This highlights the efficiency and effectiveness of OPRAG in enhancing answer quality with reduced input length. The introduction of this paper discusses the limitations of early-generation large language models, LLMs, with context windows of up to 4,096 tokens. To handle large-scale context corpora, retrieval-augmented generation, RAG, became indispensable. However, the answer quality in RAG systems heavily depends on the retrieval model's performance. Recently, state-of-the-art LLMs like GPT-4o and Gemini 1.5 Pro support much longer context windows, raising the question of whether RAG is still necessary. This paper re-examines the effectiveness of RAG in long-context answer generation, proposing an order-preserving mechanism for retrieved chunks that significantly improves answer quality. The related work section discusses two main areas: retrieval-augmented generation, RAG, and long-context language models, LLMs. RAG systems incorporate external knowledge to provide up-to-date and specific information, thereby reducing errors and improving accuracy. Prior to the advent of long-context LLMs, RAG was a promising solution for handling short context windows. On the other hand, long-context LLMs have seen significant advancements in computing efficiency and positional encoding extensibility, enabling support for extremely large contexts. Recent flagship models like GPT-4o and Llama 3.1 exemplify this progress. However, a recent study by Li et al., 2024, suggests that long-context LLMs without RAG can outperform RAG systems. In contrast, this work introduces the order-preserved RAG, which maintains the original document order and demonstrates superior performance compared to long-context LLMs without RAG. Figure 2 illustrates the difference between the traditional vanilla RAG and the proposed order-preserved RAG. A long document is divided into 13 chunks, each with a similarity score. The top 4 chunks with the highest scores are retrieved. In vanilla RAG, these chunks are ordered by score in descending order. In contrast, the order-preserved RAG maintains the original order of these chunks as they appear in the document. In this section, the authors introduce the order-preserved RAG method. First, they describe the chunking strategy where a long document D is split into n chunks sequentially and uniformly. The index I of each chunk Ci indicates its position in the sequence. Next, they explain the relevance scoring process, which involves computing the cosine similarity between the embedding of a query Q and each chunk Ci. The top K chunks with the highest similarity scores are retrieved. Finally, the authors emphasize the importance of preserving the original order of these chunks in the document D, which distinguishes this method from the vanilla RAG approach that orders chunks by similarity score alone. Figure 3 illustrates the impact of context length on the performance of retrieval-augmented generation (RAG). The evaluations are conducted on the en.qa and en.mc datasets from the Infinity benchmark. Initially, as the context length increases, the performance improves due to a higher likelihood of covering relevant chunks. However, beyond a certain point, the performance declines as more irrelevant chunks introduce distractions. Specifically, the Llama 3.1-8b model achieves its peak performance at a context length of 16K on both datasets, while the Llama 3.1-70b model peaks at 48K on en.qa and 32K on en.mc, indicating that larger models can handle longer contexts more effectively. In this section, we discuss the experiments conducted on two datasets, en.qa and en.mc. En.qa consists of 351 human-annotated question-answer pairs, with an average context length of 150,374 words. En.mc, on the other hand, contains 224 question-answer pairs with 4 answer choices per question, and an average context length of 142,622 words. For evaluation, we use F1 score on en.qa and accuracy on en.mc. The experiments were implemented with a chunk size of 128 tokens, non-overlapped. Key findings include that the proposed order preserve RAG significantly outperforms the vanilla RAG, especially when the number of retrieved chunks is large. The performance peaks at specific context lengths, such as 16K and 48K, and there is a significant reduction in the number of tokens used compared to traditional methods. Table 1 presents a comparison of the performance between long-context LLMs without RAG, the self-route mechanism, and the proposed order preserve RAG, OPRAG. Key findings include the Llama 3.1-70b model achieving a 34.26 F1 score with 117K tokens, the OPRAG 48K model achieving a 47.25 F1 score with 48K tokens, and the self-route GPT-4o model achieving a 34.95 F1 score with 85K tokens. These results highlight the efficiency and effectiveness of the OPRAG in reducing token usage while improving answer quality. Figure 4 illustrates the performance comparison between the proposed order preserve RAG and the vanilla RAG, evaluated on the en.qa and en.mc datasets using the Llama 3.1-70b model. The figure shows that while the advantage of order preserve RAG over vanilla RAG is minimal with a small number of retrieved chunks, it significantly outperforms vanilla RAG when the number of retrieved chunks is large. Specifically, on the en.qa dataset with 128 retrieved chunks, vanilla RAG achieves a 38.40 F1 score, whereas order preserve RAG achieves a 44.43 F1 score. On the en.mc dataset with 192 retrieved chunks, vanilla RAG achieves an 81.22 accuracy, while order preserve RAG achieves an 88.65 accuracy. In this paper, the authors challenge the prevailing trend of favoring long-context language models, LLMs, over retrieval-augmented generation, RAG. They argue that extremely long contexts in LLMs can lead to a diminished focus on relevant information, potentially degrading the quality of answers and question-answering tasks. To address this issue, the authors propose the order preserve retrieval-augmented generation, OPRAG, mechanism. Extensive experiments on public benchmarks have demonstrated that OPRAG significantly improves the relevance and quality of answers, highlighting its effectiveness in comparison to traditional long-context LLMs. Thank you for watching.